Okay, we have released LAMP 5. So in LAMP 5, you are going to configure the firewall use IP tables. And like always, you should start early. Do not wait for the last day. And today we will continue discussing SDN, and this will be our last module on SDN. And we are going to introduce two more concepts that have been inspired by SDN and talk about the security of SDN. So basically, this is what traditional computer networks look like. So when I say traditional computer network, I'm talking about enterprise network, data centers, not really internet. So the concept of SDN right now, we are still using it for data center, enterprise, those closed networks. We are not trying to apply it to internet, even though there are some discussions, but I don't know when that will happen, because imagine in our current SDN, there is a logically centralized controller, control all the switches, all the routers, all the middle boxes, but at the internet, it might not be possible. So all the concept we are saying for SDN right now, we're talking about enterprise network, especially for data centers used by large companies. So in traditional network, the data plane and the control plane, they are mixed together in all those hardware boxes. And administrators, they have to manually configure each of them, which is very painful. And the idea of SDN is to extract that control plane out from all those switches. And so there is a logically centralized controller or control plane. And that controller or control plane has a global view of all the network. So everything to the controller is just a graph, or maybe a directed graph, labeled graph, but it's just a graph. It's not distributed anymore. And the controller will use the protocol called OpenFlow to control all the switches. And like we said, OpenFlow is just one of the most popular, the only standardized protocol. But it's possible that some switch manufacturers, vendors, they are using their own protocols. So this figure, this architecture depicts the SDN infrastructure. So we have at the lowest data plane, we have many boxes and switches, and they only run the SDN data plane to do forwarding, dropping based on the flow tables. And the interface between the data plane and the control plane is called the control data plane interface. Usually that's the OpenFlow part. And on top of that, we have the controller, and the controller will provide a lot of interfaces for different applications to use. So those applications, they can be programmed to achieve their business logic. It could be a load balancer, it could be a firewall, or intrusion detection system. So you can see that the controller part is very important. It's the brain of the whole SDN. And right now, there are several popular SDN controllers. One of them is called Open Daylight. It's an open source controller project under Linux Foundation. And Open Daylight, so like we said, it has to provide northbound interfaces for applications to call, and it will also use southbound drivers. It supports OpenFlow and several other protocols to talk with switches. So with Open Daylight, we can develop network applications using its protocols. So this is the architecture of Open Daylight. Here is the other switches, and this is the controller part, and you can develop controller extensions, or you can develop applications on top of it. So this is one of the most popular controller we are using right now. Most companies are supporting this controller, and they are contributing to this open day-night controller. So we talked about SDN a lot, the network side of SDN, but this is a security class, and I am a security guy. So I am interested in 3 security implications of SDN. The first one is how can SDN help improve our enterprise and data center security? Can we use SDN to build some new security mechanisms or new security tools that were not possible before? And the second question we are interested in is there any challenges? Because SDN is this new network paradigm. So it does mean that we can simply apply existing security solutions that works perfect on traditional networks to the SDN network. So we are interested in to say, are there any challenges in deploying existing firewall or intrusion detection systems in SDN architecture? And also we are interested in the security of SDN itself. Are there many attack surface in the control and data plane of the SDN switches, the SDN controllers? So basically, these are the approaches we approach any new paradigm, new thing. As a security guys, we think about those 3 problems. And we're going to talk about what we have found as a society, security society so far. So first, how we can use SDN to help improve our enterprise security. So previously, we talked about the firewall and the intrusion detection system. One problem of those systems is right now we can only place those systems at the boundary of the network, the perimeter of the network. Like your home firewall, you only have one firewall that is built in your router, which collects your home network to the internet. And for companies, even large companies, they have the same. Like this is a large corporation, and they have a firewall here to collect the whole intranet to the internet. Even though in this network, there might be a lot of subnets, and at those boundary of subnets, they have their own firewall. But still, those firewalls, they are only residing on the boundary of the network. They can only monitor the traffics that across the boundary of the network. But we know that switches, they are not really boundary of the network. Routers, they are. Well, I'm talking about layer 2 switch. So switches, they are collecting the same network. They're not the boundary. So, but with SDN, so the problem of this is there might be a lot of insider attacks, insider threats. Those malicious traffic, they will not cross the boundary of network. And the existing firewalls, intrusion detection systems, they cannot be able to detect those kind of attacks because they don't have the visibility to those traffic. But with SDN, every packet has to go to a switch. Even though that switch is not the boundary of the network, then even though that switch is not at the boundary of the network, it can still see that package. So with SDN, we can put those detection rules in each flow tables of each switch. So in this case, each switch is kind of like a security policy enforcement point for us. So it's ubiquitous. It's anywhere in our network. It doesn't have to be at the boundary of the network. So this might be one of the benefits of using SDN for enterprise security. And the next question is, even though we have the high-level idea of using SDN4 firewall intrusion detection system, and in theory, it might provide a better visibility of the whole network, can we really deploy existing firewall or intrusion detection system there? So we have been studying this, and we find out actually there are some problems. So imagine we want to deploy a stateless firewall. So we only want to inspect each packet. So the open flow protocol allows switches to change those packets. And if there is an attacker who installs some malicious applications on top of our SDN controller, those malicious applications can instruct the switches to change those packets. And by changing those packets, they could possibly bypass our previous firewall rules. So let me show you an example. We have a simple network with 3 switches and a SDN controller and 4 hosts. Assume that we have a firewall between host 3, or it's a host-based firewall on host 3. That firewall says any traffic from host A to host C should be deleted. But if some malicious attackers install some malicious apps on the controller which instruct all those 3 switches to install flow rules like this. For example, any packet from host A to host D will be forwarded, and the second switch will say any packet from host A to host D, we will change its source IP to B and destination IP to C. So applications, they have the privilege to do something like this. Then the third switch will say any packet from B to C will be forwarded. So in this case, if host A wants to attack host C, it doesn't have to use host C's IP address. It will use host D's IP address, center package, source IP is A, destination IP is D. Then the first switch will simply forward that, and the second switch will change the source to B and the destination to C, and the third switch will forward that to host C. So host C will still receive the malicious packet from host A, even though it has an explicit firewall rule to stop that. So, but because of those malicious applications in the network, they can change the packets. So firewalls here were not at the edge firewalls or host-based firewalls will not work anymore. So to solve this kind of problems, we have to see the global view of the network. We have to know what has been changed in the network. We have to track all the packet changes in the network. Actually, we did some research several years ago. What we did is we developed some applications on the controller layer or application layer. So those applications can track all the flow table changes. And using some algorithm, we can compute those reachability of all those loads in the network. And by comparing those reachabilities with all the firewall rules, we will be able to identify is there any conflict in our network configurations. So the second thing we identified is it's hard to implement any stateful application in SDN. So imagine we want to implement a stateful firewall. So we want to enforce policies like packets from or to the website or web server are only allowed only if an outside host initiated the collection. So this is a stateful rule we discussed a little when we talk about the firewalls. So to enforce this kind of rules, the firewall has to remember the state of each collection. However, we know that in SDN, in open flow, each flow entry in the table is simply rule, action, and stats. So there is no collection states remembered, at least at the switch layer. So, but it can matches not everything, but a lot of things. So this is what the current open flow can match. They can match TCP source port, TCP destination port, but they do not really match the TCP flags. So, so even the current rules, they cannot be used to identify what type of packet, TCP packet is. So one way to implement this, okay, I forgot to discuss this. So also, when an OpenFlow enabled switch receives a packet, usually we will first check if this packet matches with any flow entry in its flow table. If no such rules exist, then the packet will be forwarded to the controller. But if there is an entry exist to match with the packet, the switch will simply perform the action like forward or drop. It will not forward this packet to the controller. So which means the controller will not receive all the packets. Only the switch will receive all the packets, but the switch doesn't have the ability to remember the states. We can develop some applications at the controller layer to remember states. But if we are using OpenFlow, the controllers will not see all the packets. So you cannot really do those state transitions. So to enable stateful applications, including Stateful Firewall, we developed something we call it StateMon. So in order to do this, we have to change all the switches and controllers. So why do we have to change switches? Basically, that's because the current OpenFlow, they cannot match any fields in the packet. So technically, we believe in the future, they probably want to extend to that. Any field in a packet should be able to match. But currently, no, they are only like we had here. At the layer 4, they are only matching TCP source port numbers and destination port numbers, not the TCP flags. But in order to track the TCP states, we have to match the flags. That's why we have to extend the current flow tables. And another thing is the current messages using OpenFlow that support the communication between the controller and the switches, they cannot support state transitions. That's why we also extended those messages. We call it open collection messages. Then most importantly, we track the collection states in the controller. So there are some papers that are talking about how about we just simply remember the collection states on the switch. That would be easier. So the OpenFlow, you don't need to change OpenFlow because the controller doesn't have to say everything. But our argument is that design might be easier, but it is against the philosophy of SDN. So when we do SDN, we want to clearly separate the data plane and the control plane. So if we put the state back to the switches, then switches is a mixture of data plane and the control plane again. So that's why our design, it might be more expensive in communication, but we believe it adhere to the SDN philosophy. So the third part of research is about the security of SDN itself. What kind of attacks the SDN controller and data plane they are facing. So the first problem has been discussed in many papers. All of these attacks I'm talking about today, they have been proved in papers, and some of them had a lot of demonstrations. And the first attack is called packet in flooding. So basically, you remember, if a switch doesn't have a flow entry to match the incoming packet, it will forward this packet to the controller. So, and the controller is connected to many switches. So it is possible for attackers to intentionally generate a large number of distinct network flows. So all the switches, whenever receive a packet, they will forward this packet to the controller. Because there are so many switches, this becomes a bottleneck in this SDN architecture. So this is kind of like all other flooding. This can cause a DOS attack to the controller. And if the controller is down, and the whole SDN infrastructure is down. And the next very related attack is called a switch table flooding. So basically the controller, even though the switches, they do not have something specifically called a switch table anymore, they have flow table. And the controller part, if they wanted to switch, they will maintain switch tables. And by carefully design those packets, attackers can send a lot of packets to the controllers, and the controller will inject a lot of new entries to its flow table, switch table. And because this is software defined, there is always a limit in how many entries should be there in a switch table. So this can be overflowed. And also the switch side, the flow table can also be overflowed. Usually they are hardware based, and those hardware, usually it's called TCAM. They are very fast lookup memories, but it's very expensive, so they can be easily overflowed. And also the current SDN applications and SDN controllers, the interface has not been standardized. So some applications, they can develop plugins for the controllers, which means that plugin or extension will run in the same address space as the controller process. So if there is a bug, a software bug in that extension, it may crash the whole SDN controller. And that is a single point of failure. If the controller fails, the whole system will have a lot of problems. And also the controller and the switches, they will have a special channel, control channel, using OpenFlow to communicate with each other. And usually they will use TLS and SSL to protect the communication. And as we studied before, man-in-the-middle attack is possible there to hijack the communications between controller and switches. So basically, all the software and system attacks we have been used for decades.
So do the control messages and the traffic, just the normal network traffic, they flow across the same network? There's not like a separate network or channel usually for the control messages. So if I'm on the network, I could somehow do these attacks just by being there?
So they are using physically the same channel, but that channel has to be encrypted, use SSL. But I think it's possible to do that, not physically, but how can you make that scalable? That's the thing.
If you don't, I mean, it's still using TCP then,
Mm-hmm.
so you could still, any exploit that you could do at the TCP level, whether it's encrypted or not. You
Yeah.
can't listen, but you could still
Yes.
DOS type attacks.
Yes.
So if the controller were to crash on any of these, would the switches continue to forward on the current rule set that they have?
Yes, they were.
So what about packets that don't have flows? Would those be blocked?
So,
Or would they just clutter the system?
so switches still is supposed to forward that to the controller. We just never get
So
anything
just
back
drop
from,
it.
I don't know, maybe depends on different switch. So,
Oh, it's switch behavior based.
yes,
Okay.
yes, but technically they still forward to the controller, they just never hear back from the controller what I'm supposed to do next. Yes. So, because this controller right now it's just a software running on any computer. So basically all the software and the system attacks that we have been discovered in the last 2 decades, they can be used to attack the controller. So one way to solve the problem is, even though the controller is logically centralized, we can have multiple copies of it, physically duplicate those controllers. And also at the data plane, we are facing many security challenges. The first one already discussed is the flow rule flooding, because the switches, they are using dedicated memory, TCAM, to speed up those rule matchings. So usually there is a size limit for those memories, and it's possible to fill up, overflow those tables. But technically, controllers should be able to know that, should be able to detect everything. And also, because we are adding a channel here for controller to control the switches. So previously, those switches are distributed. They don't have this, technically they still have this thing, but all those control messages, if there are some malformed control messages, and if there is a bug in the switch firmware, switch software to pass those control messages, and it may trigger some software bugs in the switch and put the switches in some unpredictable states. So basically, these are the security challenges the community has discovered in recent years. The problem of existing the switches and controllers. So, like I said in last class, so probably the idea of SDN will be there for many, many years. Even though the protocols we're using, OpenFlow, may change, but the idea to abstract the control plane from switches will be there for many, many years. And no matter you are going to get a network job or software developer job or do security in the future, you probably will hear about SDN. And so if you are interested, there is a very good reading list on SDN, not only security, but the SDN part, the general reading list. And this reading list is maintained by the Open Network Foundation, which is the organization that is supporting SDN. And they are also hosting academic conferences on SDN. So there are also a category of security papers talking about the SDN securities. They also have several video links. Some of them are like 10 years old, but very, very good introduction to SDN by those guys who actually invented SDN. So there are 2 concepts or paradigms that have been inspired by SDN, and they are getting very, very important recently. The first one is called network function virtualization. So the basic concept is previously all the network devices, no matter it's a router, it's a switch, or it's a firewall, or we have content distribution network servers. So all those network devices, they have been hardware based. They are baked in hardware and hard to change, not flexible, hard to update. So the idea is with the help of cloud, can we just virtualize everything? So all the switches, firewalls, intrusion detection systems, they will just be a virtual machine in our data center. And you can see this is highly related to the concept of SDN, but they are not necessarily tied with each other. For example, one of the very successful network function virtualization project is called Open vSwitch. So basically this project is they developed a totally software-based switch. So the switch is just a virtual machine in your data center. And actually this is what we are using for the ThoreSnap. You are using for all the maps. So this is a totally software solution, no hardware there, everything is just a virtual machine. And this is a network function virtualization, but this is not really SDN. So SDN and NFV, they complement with each other. So imagine you have a data center, and sometimes you need switches, and that switch can be a virtual machine. But that switch can be a traditional switch in a virtual machine, a layer 2 switch, or it can be a layer 4 switch. But it can also be a open flow based switch. But we're not talking about hardware anymore. So an open flow based switch can also be a virtual machine in your data center. So that is how they can be combined together. But those are kind of two separate ideas. So SDN is more about, I want to abstract the control plane from the data plane, and network function virtualization is about, I just want to put whatever network function in a virtual machine. So they do not conflict with each other. And you can see that the OpenSwitch project, we can use OpenSwitch without SDN. So the OpenSwitch doesn't have to be an open flow based switch, doesn't have to be a SDN switch. So network function virtualization is actually happening with and without SDN. So a lot of firewall and intrusion detection systems, they have been put in virtual machines. But those tools, they are natural allies. So that's why currently if you follow all the news and read the papers, they always come together. SDN and NFV, they always come together. So the second idea inspired from SDN is called software-defined infrastructure. So this has been, NFV has been there for like maybe 5 years. SDN has been there starting 10 years ago, and this SDI is a new concept, I say maybe this year or last year. So, but this is highly inspired from SDN. So in software-defined networking, we're trying to abstract the control plane of network devices from the data plane of network devices. So the concept of SDI is very similar. They want to abstract the control plane of any computing resources out of its hardware. So there will be a new software orchestrator. It's kind of like the controller. And this one controller will automate all the infrastructure provisioning and configurations. So this is a figure provided by Intel, I believe. So they treat all those computing resources, including storage, network, and CPUs, as a resource layer, as resource pool. It's kind of like the SDN idea that we have the switches at the data lane, the data plane, they only do forwarding, dropping, and those layers, they only do storage, forward, or compute. But there is another layer of orchestration, like the controller, will abstract everything. So as a developer, you can develop softwares on top of this. So you develop application A, and you don't need to worry about where application A is running. And you don't worry about what kind of network resources application A is going to use. Everything is transparent to you and orchestrated by this software layer. And so if we say the network part is very similar or exactly same as SDN, they are adding computing and storage there, which is the new contributions from the SDI part. Yeah.
So how is this kind of different than platform as a service?
So this is a platform as service. So it's very similar, but I think platform as service, we are still mainly talking about the computing resources. Yes. Here we're talking about combining everything together. So this is more like inspired from SDN, but directly from cloud computing. So this is something the companies, the big companies like IBM and Intel is really pushing this year. So they are all inspired from SDN. Any questions?
Yeah. So would something like this enable you to kind of have a set of known states for your switches and everything to basically have some kind of checksum, and that way you can tell if it's been changed in any way maliciously and just like shut that off and open a new instance of that switch if it's a virtual machine?
Yes. And this layer, typically you can do all kinds of security checks.
Okay.
But from the developer side, you don't really know which machine this is running, what network is running. You don't need to care about that. So you can see here, let's think about security. Any other questions?
Do you think the long-term adoption of this is going to be like 15 years?
I don't know. I think it could be super fast. Because all of this, we're not talking about internet scale. We're talking about more enterprise and data centers. So some company, a large company, they can outsource this to IBM to do that. Then it's just happening in several months. IBM may already provide a service like this. And if ASU wants to upgrade their infrastructure, they can outsource to IBM. Or something that you know this. Yeah. So not 20 years. It's already there. They are selling this now. Okay. If no other questions, let's meet Wednesday again.